Hello guys, how are you? How's it going? Hello. I'm just testing my audio right now and my video to check that everything is good. Yeah, apparently we're 19 minutes live already, 19 seconds live. So that's good, I guess. I'm just gonna check that the audio is good. Apparently we're 19 minutes. Sure, that's good. Perfect. So I just came back from walking my dog, taking a shower. And right now what we're gonna do is we're gonna continue with our embedded course. Just in case, just to summarize, so far we learned how to transform text input into a numeric format, so we can get the semantic meaning of any text. So that means that, for example, if I have two texts, one is like, what is the directions of to go to the cinema, or in which way can I go to the cinema? Like, both of them are asking you basically the same, but if you compare word by word, it would be really different. But if you transform that, embed that, and get its coordinates in a multi-dimensional space, probably they will be really close to each other. So that's the whole concept of embeddings. So now we're in an exercise. You're seeing my screen, and now we're gonna see this. Okay, you have been provided with a list of dictionaries called products, which contains product information. And for different products sold by online retailer, is your job to embed the short description for each product? Here's a preview of, okay, we have the products, and it's a list of dictionaries. So create a list called product descriptions containing the short description for each. So here is, okay, so creating a base for short description. Okay, product embedding. I should get the response date. Create embeddings for each product. Using batching and passing the input to the text embedding 3 small. Extract the embeddings for each product and add it to the response. From the response dictionary and start doing products. So I should just get the embeddings for the product description and put it back into the original dictionary under the key called embedding. So yeah, so basically here I should get the products have been defined. So this is products. Then the way to iterate on this, please autocomplete this in Python. So if product is a list of dicts with a description field, it should be like this. If it's a list of objects, it should be like this. So basically it's a list of dict. So I should make product, and then here I should put the short description for each product in products. If it would be a list of objects, it would be like this. All right, and then here I should do this because the client's already defined. So I should do this. Text embedding 3 small, and then here I should do this, I assume, but I'm gonna ask, is this correct? Because I don't know if the input is accepting an array. It's conventional description for this, the embedding right called create and accept a list of strings as input. Okay, so it's good. So I can accept a list of strings there. Wait, I'm gonna check the audio is good. Yeah, it's good. And so in the response model dump, I got an in this response dict. What I was getting here was first I was getting a, give me 1 second because I'm just gonna check if I'm getting an array. No, so if I'm passing an array, then it should be the response should be an array, I assume. So for product in, again in products, response dict, I should get the item from the response, the index of the response, and then inside we had the uh, data 0 embedding. Yeah, and then print product items, and then here it should print the here I should print the what is this called, all of the items in each product, which is like the, apart from the server description and apart from all of the other fields of the product, I should also print the embedding. So let me run this, and there was an error, too many values to unpack. Okay, let's explain this. Each item in product to variables is a list of dictionaries. Each item is just a single dictionary, not a tuple. Aha. So I should do here enumerate. Product embedding. Aha. So because of the fact that in the previous one we were only having one input, it should be always 0, but in this case that's why it was, so it should be data, and this I should be here. So then I will get the, yeah, that's correct. And then so if I'm passing an array, I should always go inside of the data, and then inside of the data I have the array of in this case I get the 0 because there's only one element in the input, but if it's like an array I should get the index and then the embedding. So I should submit the answer now. So that's perfect. So let's just copy this here. So 3 underscore this is going to be called the embedding product descriptions, and in here we're going to paste all of this. Then from here we are going to tell this to clear to, and then I wanted to expand on this file. Please expand. Please define products so the Python file can run correctly. Yeah, and it will create a product with all of make sure it is only 4 to 5 products just for testing. So because I don't want to have like a really huge list of products, because then I don't want to use too much of my tokens. I just wanted to make sure that I can get the proper results here. I'm also gonna ask here. Yes. All right. Okay, why this line is correct and this line incorrect. Yes. And okay, each iteration gives you one item. So the iteration was good. Okay, the problem here is that when I iterate in here, two variables, so I cannot destruct it. That's why it says like can unpack each item into 2 parts. So basically I am creating a enumerate which wraps the list and yields and creates at least an item. Okay. The common pattern in your embedding will be 4 product embedding ownership. Okay. So anyway, it ran good. Now I'm gonna do the Python 3, and here I'm gonna just put I'm gonna just print the first one, which will be that this is a smartphone with the features, the description, plus the embeddings. But anyway, I will just execute my text will be all of that, but this doesn't mean that I just call for the first input. I call for all of the items, but I just printed the value of the first one. That's cool. All right, guys. So let's jump into the next one. Visualizing the embedded descriptions. Now that you created embeddings for the product descriptions, it's time to explore them. You'll use the TSNE to reduce the number of dimensions in the embedding data from 1536 to 2, which will make the data much easier to visualize. You will start the products list of dictionaries. You work in the list containing the product information and the embeddings you created from the description. As here, remember, here's a preview of the products being imported as PLT and MP. Okay, so the categories. Here I'm iterating for each one, and I'm getting the product. In this case, it will be category here, and in here will be embeddings here. Then numpy have been imported as PLT. Okay, PLT has been imported and then create list by storing the. Okay, I have the tool list here. Okay. So here's embedding. Okay. Okay, that's good. And now reduce the number of embeddings dimension from 1536 to 2 using the TSN. So here's the TSN. Here's transforming it from 1536 into 2. I don't know what should I call there. TSN fit transform and NP array. I should pass just the embeddings, I assume. So I should run it and I should submit it. And this is good. And now create the scatter plot. So okay, so I should do this. What it should be the first column, and it should be the second column here. All of the rows the first column, all of the rows the second column, and then yeah, the y-axis, and then do plt show, and it's gonna show this. So yeah, more or less like the categories. I embed the description, and if you see, like, it has similar categories, so it's quite nice. Now I'm gonna submit, and now I'm gonna create another file here called rename 4. It's gonna be called visualizing embeddings. Okay, and in here I already have this, so I'm gonna do this at the end, which is going to be, instead of printing this, I'm gonna create the plt show. And first I'm gonna do cover on this file. Can you import the missing dependencies? Because in here is already defined the PLT and NP, but I need to import this matplotlib pyplot as PLT and numpy as NP, I think. I'm just gonna check what it gets here. Scalar manifolds, yeah. Okay, so yes. So the TSNE to reduce the dimensions, the PLT for plotting. Perplexity should be less than the number of samples. Okay. The perplexity equal to, why should it be less than the number of samples? I'm gonna explore here because there are some parts of the code that I haven't checked before, or I have checked like long years ago. No, what happened? Okay. By looking at each point and asking who are my neighbors. For every point, it builds a probability distribution over all of the other points, where nearby points get high probability. Perplexity is the effective number of neighbors each point should consider. A perplexity of means treat each point as having about 5 minimum neighbors. Now count what's available. With 5 products, each point only has four other and the entire data set. You can ask a point to consider 5 neighbors when only 4 exist. Okay, that makes sense. Neighbor distribution has no solution. Okay. Internally, the T-SNE searches for a bandwidth, Gaussian sigma, for each point, such as the entropy of its neighbor distribution matches the log perplexity. And the maximum entropy possible is n minus 1 neighbors in log. A typical recommendation is perplexity between 5 and 50, but assumes hundreds of thousands of points, which tiny data size you're forced to go lower, hence perplexity. Seriously, use a sanity check that similar categories land each other. If you later restore the full data camp prog list, perplexity 5 becomes a valid, again, a reasonable choice. Okay, it just makes sense. Can you add this comment explanation at the end of the file? Because I just want to keep track of it. Also, I'm gonna check because this line is basically just transforming a list into an array. This one. Embedding is a Python list of list. 5 procs, since the text embedded into a small dimension, and an NP array converts it into a numpy to the array change. Okay. There is a reason it's neat that it expects an array like in specific samples and features. Monocyclic lens will actually accept the plain list of lists and convert it internally. So the explicit conversion here is partly stylistic, but it's good of it because it makes the shape explicit. Because that doesn't exist on a list of lists, the shape. But in the end, when you do the MP array embeddings, you can get the shape. It's a real data structure change, not just a cast. A list of lists scattered points to Python float objects all over. The numpy array is like one contiguous block of raw numbers, which is what makes the vectorized math inside. Okay, so it optimizes too. So it fails loudly on by data. If one embedding has different length, the conversion will produce a warning error instead of the mismatch surface difference inside the circuit. Okay. Information that just a little, but under the hood it changes how the numbers are stored, not just the type that wraps them. Okay. Also add this explanation at the end of the file. Then also the other thing I wanted to check is so you get here the embeddings in 2D. Yes. Then this is confusing me a lot, but can you explain what does it do? What does this line does? Because so as far as I understand, this is an array of down to 2, yeah. So a smartphone is like so like all rows and 0 means column 0. So it's basically, so if it will be 3 dimensions, I will just get this row 1, the column 0 and all of the rows. Okay, so you will handle it better with NP-array because otherwise I will need it. I will need this. Cutter will be like a list of x, and so it's like coordinates in the xy. First the map by element and draws a dot on each position. So product I becomes the point, and the first product lands at 12.3 minus 4.1 and so on. Okay, I got it. It just invents two coordinates there. It's just like abstract. That's why. Okay, and then in the annotate, in the enumerate, so it enumerates the categories, and then in the PLT I annotate the category, and I'm gonna go to the position, right? So to that position, I'm gonna put the category, which is a text. Okay, so just to confirm, okay, so this line just writes the text category into the coordinate where the product I is. This exactly. So you got the text and the position. It's a tuple there. And the place string text position area. The right top of next to the dot. Can overlap. Okay, and then I need to do. I'm just gonna run it now. Whoa. No, I close it here and I wanted to close it here. Okay, I'm gonna do this. I'm gonna run this. Maybe I'll just check if there's some libraries missing here. Normal sklearn. So I should do pip install -user sklearn. Here I'm waiting until this loads. I need to get a new computer. This is getting super slow lately. And it's gonna get slower and lower during the next few months. So I need to get a new one, I think. If you guys have any recommendation, I'm doing full stack development, and now I'm doing AI engineering. Possibly, I'm gonna start doing machine learning too within the next few months. So I will need super strong machine. So I'll need your help. Ironically. So Python setup egg did not. Okay, I'm gonna ask here what is going on. Okay. This is an issue the package mentioned and not pip. What is this issue about? You know, normally in the past I was going to Stack Overflow or just go Google some of these problems, but now the cloud can solve it all, almost all. All right. Okay, so the library is called sklearn, but the pip package name is scikit-learn. Okay. Why did this? It's a bit confusing. Now, let's learn. I think when we start doing the machine learning, deeper, we can just come back to this thing, because this is something regarding probably we need to go deeper in math and probabilities. So we'll need to unfold some packages of some things from the university, maybe some books, because this is already more complex. If we're talking about if we are checking the Gaussian sigma, the entropy, we need to if we want to really understand that part, then we'll need to go deeper into math and probabilities. So not this month, maybe in the next month. All right, just in case, because probably many of you will want me to explain that right away, but it's not the time, guys. We need to finish this course with path of AI associate engineer for developers, do whatever is planned, and then we jump into machine learning. Now let's run the Ford. And it did. So kind of like it transformed it good. It's close the categories to each other. If we will have more data, it will be much more interesting. But as far as we don't have the data yet, we cannot see it. Because we also, if we put more data, that will mean that we will run more tokens, and we don't want to do that at the moment. But so far it worked. Let's submit the answer and check. So it's good. And now we can continue to the next exercise. So let's just close this. And here we're gonna do the text similarity. So this is the part in which the embeddings is gonna work, because this is gonna be useful to do semantic search. So let's listen to this.
Let's round out the chapter by looking at how we can compute the similarity between two pieces of text using embeddings. Recall that embedding models map semantically similar text more closely together in the vector space. This means that we can measure how semantically similar two pieces of text are by computing the distance between the vectors in the vector space. Being able to measure similarity is what will enable the embeddings applications we've discussed previously: semantic search, recommendations, and classification. There are many different metrics for computing similarity in higher dimensions, but we'll be using cosine distance. The cosine distance uses linear algebra, a branch of mathematics, to evaluate the similarity between two vectors. Let's start with a small example of 2 points in 2 dimensions. To compute the cosine distance between the 2 points, we can import distance from scipy.spatial and call distance.cosine, passing the coordinates of the 2 points. The result is 1. This is difficult to interpret on its own, but the distance can range from 0 to 2, where smaller numbers indicate greater similarity. Let's try this out with text embeddings. Let's return to an earlier dataset of with text embeddings. Let's return to
Wait, I need to remember what was the distance cosine, okay? Because it's been like so many years since I haven't done this explain cosine. And then I'm gonna do it. Explain distance dot cosine of 0,1 and 1,0. So cosine of 0 is in the same direction. So that's the cosine of 90 is perpendicular. Yeah, because this is like something like this. Here's the angle. If it's 0, it's 1/1. So it's, well, it's 1. But if the angle is like this, it will be basically the triangle will be like this, and this part is 0. So it will be 0/1, which is 0. And if it's in the other side, it will be -1/1, which is going to be -1. The other angle, which is 270, 0, 360 is still 1, which is going to be 0. So that's the cosine, but the cosine similarity that takes the idea and applies that to vectors. Okay. How apart are these points? That's the Euclidean distance. It does do these two vectors point in the same direction. So I'm gonna do the vectors. I'm gonna do the point multiply, and then the absolute value of vector multiply. So I don't know if here they are explaining it correctly, you know, because this is a dot product two vectors divided by the product of their length. Dividing by the length is the key trick. It normalizes away the magnitude, so only direction matters. Okay, so in this case, what we are checking is the direction only, because this can be here and this can be here, and it's gonna probably return you the same. Values typically fall between 0 and 1. Most embeddings model plus 0 point means most embeddings model produce vectors where negativity similarity is rare. Okay. Near duplicates related topics 0.1. Below 0.1 usually means related. Why not just distance? A long document and a short sentence about the same topic can be far apart in Euclidean terms, different magnitudes. The point in the same direction, cosine, ignores line, which is exactly what you wanted for about the same thing. Okay, but something that I need to check here is like, can you yeah, it was doing this, but so in this case, in the case of here, I think we're talking about two different things, because this is going in one direction, this is going in one direction. The cosine of this is going to be basically, wait, no. So what does the dot prog does? This is from university, so long time ago. What's the degree operation? Mechanically, it's that simple. Multiply the vectors, okay, and environment, sum everything up. But the meaning is the interesting part. Think of each dimension as a feature. When both vectors have big value in the same direction, that term contributes a lot to the sum. When one has a big value, whether the other has zero, the term contributes nothing. When they have opposite signs, the term subtracts. Geometrically, there's an equivalent definition, which is the magnitude of A and magnitude of B times the cosine. Yes, which says that the product measures how much of a vector lies along the direction. Of the other project, so it's the projection of A onto B. Projection of A onto B is the A cosine B. It's the A cosine of theta. Okay. So what we're doing, A dot point B is the okay. Perpendicular to the product 0, opposite directions is negative. So the dot product gets the this build up raw dot, which is normalization is strict. So what we're doing is multiplying the vectors and normalizing them. So if the dot product does a b cosine of theta, which is the angle, and then the we're dividing that by the a plus b. Basically, we're just getting the cosine of theta, which is basically it's like how apart in angle is one from the other one, which
Let's try this out with text embeddings.
okay, so in this case, if they are completely perpendicular, that means that like here, if they're like this, basically the angle will be, yeah, if they're like 0, the angle will be like 1, but if they're like these, they're in complete differences, so that will be of 90, which technically will be 0. Yeah, because this line here that is like the this one here is going to be the hypotenuse. So this is going to be 1, and this is going to be, doesn't matter how much, this is going to be 90 degrees and the cosine is going to be 0. So it's just basically calculating the distance in cosines, but normalized. Okay, I got it.
Let's return to an early.
So this is gonna, in this case, I'm gonna get the similarity, despite, for example, if those vectors are in the same direction, but one is like super far in the infinite and the other is gonna be like super close to the center of the origin, then they're both are gonna return us the same result as if it would be like not in the infinite but somewhere closer, because we're just checking the distance of the vectors in cosine in angular terms.
Let's try this out with text embeddings. Let's return to an earlier dataset of news article information, including headlines and topics, which are stored in a list of dictionaries. The article headlines have already been embedded using OpenAI's embedding model and stored under each article's embedding key. We'll use these embeddings to compare how similar our headlines are to another piece of text and find the most similar one. To create embeddings in a more repeatable way, we'll define a custom function to send a request to the API and extract and return embeddings from the response. This function can be called on a single string or on a list of strings and always returns a list of lists. To just return a single list of embeddings for the single string case, make sure to zero index the function's result. First, we'll import distance from scipy.spatial for the cosine distance calculations, and numpy to access its argmin function, which returns the index of the smallest value in a list. Let's start with a piece of text to compare to our embedded headlines. Computer. We start by embedding this text using our create embeddings custom function, remembering to zero index the result. To find the most similar headline to this text, we'll loop over each article, calculating the cosine distance between each embedded headline and the embedded query. We start by creating an empty list to store our distances and loop over each article in our articles list of dictionaries. Next, we calculate the cosine distance between the text and headline by calling distance.cosine, passing it the embedded text and headline. Finally, we append this distance to the distances list. The most similar headline will have the smallest cosine distance, so we can use numpy's argmin function to return the index of the smallest value in the distances list, then use it to subset the article at this index and return its headline. There we have it. The most similar headline to the text computer was one about a new tech product. Pretty neat. And now it's your turn.
Got it. Now it's pretty clear. Okay. So to identify the most semantically similar text, you need to apply a distance metric. A popular choice is cosine distance. In this exercise, you've been provided with 4 vectors A, B, C, D. It's your task to find out which vector is the most similar to A. Distance has already been imported from scipy. Spatial. So I need to get the I need to go to the part that says here, text similarity. So here we have the embedding. So we need to copy this part here, and in this case, oh, okay, so I should do distance that cosine A, B. I'm just gonna copy this here, and then I'm gonna click on it later. Then I'll do similar A dot C. No, C. So the D, and then so the distances of the cosine. So if it's like closer to 1, that means that it's super similar, but if it's like 0, so technically, technically, the closest will be 0.2, but it's not that close. So I will choose C. I'll submit the answer. Wait. Yeah, A and B. I mean, but it's saying that the mean, right? So the mean will be the 0.08, which is gonna be the D. So, but why does the closest ones are to 0 are the most similar? This is confusing because I think that if it would be the closest one to 1, the angle, it is going to be 0, and the cosine. But okay, so maybe, so what does this function does? So then that function is giving you actually the cosine, the angle, not the. Okay. Doesn't cosine. It does 1 minus it. Okay. So if distance cosine distance is identical, because it will be like 1 minus 1. So perpendicular is gonna be 1 minus 0, which is gonna be 1. Opposite directions, minus 1, minus 1. Mm-hmm. Now related another two pointing in opposite directions. Okay, so this is good doing distance 1 minus distance. Okay, so if it's in opposite direction, if it's the same, it's gonna be 0. If it's in perpendicular, it's gonna be 1, and if it's in the opposite direction, it's gonna be 2. That makes much more sense. And now let's continue to the next one. Okay. More repeatable embeddings. As you continue to work with embeddings, you will find yourself making repeated calls to OpenAI's embedding model. That will output embeddings for any number of text. In this exercise, you will just do that. Find yourself making a repeated calls to OpenAI embedding model. To make this call in a more repeatable way, it will be better to define a custom for call. Yeah, that's good. So here, wait, I'm gonna 5 embeddings I'm gonna create this one because this might be really confusing for some people who actually, if this is something that you might take at the first years of the university. So I'm just going to delete this from here. This is gonna be on the embeddings. This is from here. And then in here, in the forward, we're having articles. Okay, so I'm gonna do this, copy relative path on this file. Please expand the code so it is self-runnable. Also add comments. Because I need to generate like 5 different articles, something like that. Then create the embeddings for them. Then make a search term because I am the search embedding, and then calculate which one is the closest to 0, and that's the closest one to the search. I'm just gonna make sure that I'm just gonna let it run first, and then I'm gonna save this here. So let's see what it does here. So it's importing the SciPy spatial distance, then it's creating 5 articles with topic, then it's creating the embeddings. Right. Input is text, but I don't understand. Okay, I'm gonna do this, but why is it creating? Don't save. Here's a comment, I think. On the conditional script. So it's passing the inputs. Zip article and articles. It's gonna get one of the article and one of the embedding. Zip article, okay, and then search text, create embedding. Search text 0, so it's gonna embed the search. Distance cosine. Then it's gonna print the mean one. And then if I run the Python 5, yep, it's printing here the category, the title, and the closest one to. Yeah, this was the smallest 0.7. Okay, I got it. And now I need to do a second exercise, which is called more repeatable embeddings. I start making a repeated calls opening embedding model to make so create embeddings. So in this one we're going to in this case we're gonna call the client embeddings create, and the input is gonna be this text, then return response data return embedding, and it's gonna return you the list of embeddings, and then so I'm gonna do this, embed the short descriptions, and so I should do this. So for both, for show description and list of descriptions, so I should do this, then run the code. It ran both of them, so I'm gonna submit. Incorrect. What? Can you check the first argument? I'm gonna take a hint. Recall the list of embeddings. Do I keep the response? Okay, wait 1 second, because I think so I did that correctly, but why is it so instead of data I'm gonna get like an array, and each array I should get the, so this is an array, a list, and I'm just gonna need to get the property embedding. But because here's short description. Yeah, so in this case, yeah, I need to, so that's why. Yeah, okay, because this was just a short description. She was just one, basically. Got it. So let's do this. Let's do the let's do this is the number 6, right? Here 6. Then I need to copy this here. Then I don't need distance in this case. Then I also don't need numpy here. Then I need to now expand this file so it can be run, because here we're needing a short description and a list of descriptions basically. And so let's wait. Yep. Descriptions. First 5 values and a single one vector of the longitude of the embedding, and there's the first 5 values. And then descriptions embeddings, I'm gonna get description the first until the 50 character. Then I'm gonna the first 3 values of the embeddings are this. Okay, that's good. Let's continue. And okay, so just in case, now we need to now we're going to create a second function here, which is gonna be called create embeddings. And in here we are going to put this function, so we can just import it in the next in any other like file that we run. But that means that here I need to do this. I need to delete this. Then this is gonna need the other library that we also created. Then yes, that's correct. So now it's all self-compacted. So now we can use this create embeddings in any other file. That's pretty much. And now we are gonna, now that we have defined that function, now we are going to do this exercise, which is finding the most similar product. So we're gonna do the 7. It's gonna be 7 finding similar product. And then we are being able to compute similarity between embeddings is a key step with embeddings. You return to the products list that you worked with previously, which contains embedded short descriptions. You will also create a layer there. You will compare a piece of text of these embedded descriptions to identify the most similar description. NumPy has important distances available from SciPy Spatial. Our create embeddings function has already been defined for you and is available to use when creating embeddings from a single input. Okay, so search embedding. Okay, yeah, we're gonna do this. We're gonna do the create embeddings from the search text, and this is gonna be, because it's in an array, it's gonna be 0 because there's only one. And here I'm gonna do the it's gonna distance that cosine, the search embedding, and here is gonna be the wait, but from where I'm supposed to get the, unless it's the, where is the query embedding? Only there. So I need to, I'm gonna take a hint, okay? Because okay, I'm gonna print the keys, because maybe inside of it is already the, so it's in embedding already. So product embedding, and then here I'm gonna copy the mp arc distance is gonna give me the index, and then I'm gonna have the product. So I should print the products, and it's gonna be here the mean distance index, and here is going to be the short description. And then I run, give basket full of relaxation goodies. So this is the most similar to soap. Let's submit this. So it's good. And then we're going to do the same here. We name this 8, and this is called, this was already here. Yeah, in the 7. So we should do here from this file import. I assume that the function is renamed the same. Yeah, create embeddings, and then here we need to, we have the create embeddings, and then we don't need this function here anymore because it's already defined outside. Then we can paste this all here. And then I'll do the here relative path, here 6, and then in the 7, please complete this file so it is runnable. Because here we still will need to do the to define the products with already the embeddings inside. so we don't make a duplicate call. This is really interesting. It would be really interesting when we need to do this in the database. Uh, uh, just in case the so we don't need to create function inside. Yeah, because it was trying to create the create embeddings, and we don't need that. Because we already have it in the other file. So yeah, we have the product features and descriptions, and then I'm putting the descriptions inside of the embedding, then creating the embeddings for the. So this is like, this was the same, and it's all good except I just want this, because in this I'm doing the search queries like this, and then the most similar product is the product mean distance index or description, or products rank by similarity arc sort, which is going to be the distance, print distances index, and it's going to print the product title. Oh, that's good. I think it's good. So it worked. Why it failed? I don't know. I thought it was failing, guys. This chapter was good. It was really nice. We learned how to make embeddings. We learned how to calculate distance. And therefore, if some products have similarity or not. Of course, this one we only use the cosine. I don't know if there's other functions like sine or I have no idea. We'll need to check that further. But let's just stop here for now. I think we created now. Well, let's review. We learned how to create the embeddings, how to manage which properties the response has. Then we make a batch to send not multiple requests but a single request. Then how to visualize the embeddings in the 2D in a pie plot. Then to calculate the cosine distance between different embeddings to check if they're similar or not. Then we modularize these create embeddings because we are not going to create each one of them each time that we're creating a file. And then we put it here inside of this file so we can just import it. And in the 7.1 we already just imported it, and we made a sample of how we can just use it right away to calculate which product of this list it's more similar to the search term, in which this case the search term was called soap. So that's all for today. I think we're not gonna stream anymore because we need to work. But thank you very much. It's been always a pleasure. I'm gonna push this to GitHub so you can just check it there. And yeah, see you tomorrow.